Alright, so we had the problem from 1992. First of all, we're looking for the torque or about the axis immediately after the bug lands on the sphere. So basically what's happening in this problem is you have an axis here with two masses of mass m. We can assume that they're point masses and that they have no radius. We can also assume that the rod they're attached to has no mass, so it has no moment of inertia. And it says a bug of mass 3m lands on one of the masses, one of the original masses. And so what we want to find is the torque immediately after the bug lands on that sphere. Alright, so what we can do is we have force of gravity 1, which is the force of gravity for this side, so the sphere plus the bug, and you have force of gravity 2, which is just this one mass. So for force of gravity 1, you know it's 3m plus m times g, because you have this m plus this 3m of the bug on top of it. So Fg1 is equal to 4mg. Fg2 is straightforward, it's just this mass times gravity, so it is mg. So the assuming torque, it would be, since this mass and the bug is trying to turn its contraction this way, and this is trying to make it go this way, you have to subtract one from the other, and according to our sign convention, this way is positive, so this one is going to have a positive torque, this one is going to have a negative torque. So we know that torque is equal to the force times the radius from the axis, which we know is L, because we know that from here to here is 2L, so half of that is just L. So we know the sigma torque is equal to Fg1, which is this, times R, which is L, minus Fg2, which is the force of gravity on this, times R. So it's 4mg, which we know, minus 4mgl, minus mgl, and we get the total amount of torque is 3mgl on this contraption thing. Alright, the second part of the question is we want to determine the angular acceleration of the rod sphere bug system immediately after the bug lands. So we know that torque is equal to the moment of inertia times the angular acceleration. So we can use that to find the angular acceleration. First, we can divide both sides by moment of inertia, so we can get alpha by itself. So we know alpha is equal to the torque divided by the moment of inertia. We know torque from the previous part, from part A, and moment of inertia, because you have 4m and m, and we can assume that the radius of them is negligible. We can assume that they're all point masses, so it's just the amount of point masses times the radius. This point mass times the radius squared, so it's just 5ml squared. And then we can simplify, and we get the angular acceleration is equal to 3g divided by 5l. For part C, we have a new picture, we have a new setup. This is when, after a little bit, and after the bug lands, and this thing goes down, this part goes up, and now it's vertical with some velocity this way because it is moving this way. So part C is asking for the angular speed of the bug. So for here, we needed to use energy. So we have a before and afters. Before, which is up here, we have 3mgl because it is mg times the radius. Times the distance times the height, and we know that the height is L because this is our 0 point, and this is half of the diameter, which is 2L. So we know that is 3mgl plus mgl, which is just this rod. 3mgl is just for the bug. So you have plus mgl, which is for this mass, plus another mgl, which is for this mass. So you get the total gravitational potential energy is equal to 5 mgl. For our after diagram, we have that this mg2l is up here because this is now double, and this has no gravitational potential because it is at the 0 point. So we can write it out that gravitational potential energy in the after diagram is 2 mgl. But we also have kinetic. So our angular kinetic is equal to 1/2 the moment of times the moment of inertia of the center of mass times the angular velocity squared. And so that is equal to 1/2 times 5 ml squared, which we found over here, times the angular velocity squared. And since we're looking for the angular velocity squared, that's good because we can find it. So then we know because so we work in the non-conservative force is equal to the energy final minus the energy initial, and that's going to equal 0 because we don't have any forces outside of the system. So the final energy is going to be equal to the initial energy. We know the final energy from here, which is just going to be this energy plus this energy, and that's equal to the initial, the before amount of energy, which is 5 mgl. Then we can solve. We're looking for the angular velocity, and after we do a little algebra, we get the angular velocity is equal to the square root of 6g divided by 5l.